Good morning, students. In this video, we are going to see that CFT. So, last class we are saying that VBT is nothing but a valence bond theory, but CFT is nothing but crystal field theory. So, Unit 5 Coordination Chemistry. Today we are going to see that crystal field theory. In this crystal field theory also, like that, we are having some of the assumptions like fully depends upon the central metal atom and ligand. The bond between the ligand and the central metal atom is purely ionic. The central metal atom or ion and the ligand are considered as a point charges. What is meant by point charges? Point charges is nothing but whether your metal is having any charges plus or minus outer side, whether your ligand is having any plus or minus in outer side. Especially this metal, I said earlier, we are having a plus charge. The ligand is having a minus charge in outer orbital. Okay. See, this is inner orbital. This is inner orbital for ligand. This is outer orbital for metal. This is electrons revolving the outer orbital. This is going to helpful to repulsion or bond formation. Then this is a outer orbital for ligand. So this is a outer orbital for ligand. Now the ligands also having the outer orbital electrons. So this is revolving around the nucleus. This electron also revolving around the nucleus. So how the metal to ligand bond formation will be happen means the plus charge of metals is going to attracted by the minus charge of ligand electron, that is called outermost electron, is attracted by the plus minus the opposite pole charges. So only it's give a attraction. This give a attraction. This attraction is leads to a formation of bond. So here in the outer orbital of metal, in outer orbital of ligand, the electron is there. So this electron is having a minus, this electron also having a minus. So minus into minus, this leads to a repulsion. It's lead to a repulsion. What is happening while we are repelling the electron to ligand? This splitting into the d orbital. Why the mainly focusing on d orbital means in transition metals or coordination compounds is fully depends upon the bond formation of d orbital. So the ligand electrons entering to the d orbital, finally the splitting will be occur due to the electron-electron repulsion. This electron-electron repulsion, we are go through that how their electron-electron repulsion will be occur while the ligand is donating a pair of electron to the central metal atom. This is the structures of d orbital. You see the d orbital here, dxy and dyz and dzy. This is the in between the axis molecule, in between the axis orbital is dxy, dyz and dzx. See, this is a center, this is a xy, the in between the orbital, your orbital is electron is revolving. Since this is also in between the orbital revolving, that is better understanding. I'll show that the 3D diagram also, but you can assume the dxy and dyz, dzx is here in between the orbitals, in between orbital, and then dx square minus y square and dz square along the axis orbital. So here we are having a two sets. One is the in between set, another one is the along the axis set. So in between set of orbital is called a T2G. Then this along with the axis of orbital is called a EG. The T2G and EG is derived from the quantum numbers as well as the energy of orbital. That in your college or you are going to the higher studies, you are going to read that quantum mechanics calculation. This is helpful to identify the distraction of orbital, whether that level is D2, T2G or EG. See, The two sets of orbital is helpful to identify the which is more going to the more splitting, which is going to the more splitting. Then hypothetical steps. So first you can know understand the crystal field theory is helpful to identification of splitting of d orbital. How the splitting will be occur? Yes, step 1. An isolated gaseous state, all the 5 d orbital. What are the 5 d orbitals? dxy, dyz and dzx and dx square minus y square and dz square. So all the 5 d orbitals of the central metal atom is degenerate. Degenerate is nothing but this normal ground state, nothing will be happen. Supposed to be that the electron will be approaching the electron, that energy will be little bit higher. Finally the electron is donating a pair of electrons, the distortion will be taking place. So that is called the energy will be degenerate. The energy will be degenerate. Initially the ligands from the spherical field, a negative charge around the metal. In this field, the energies of all 5 d orbitals will increase due to the repulsion between the electron of the metal and the ligand. Okay, it's nothing but the normal ground state is there for nothing at a metal ground state. I said the earlier BBT, the metal is there. No, a pure metal is nothing will be happen. But the ligand is coming nearby, the energy state will be little bit higher. Suppose the electron will be donating, accepting from the ligands means the distortion will be takes place. So the distortion takes place means the complex formation is over. Step 2. The ligand or approaching the metal is actual bond direction. Actual bond direction is nothing but I said this earlier in the CBBT also, the head to head collision. Head to head collision or head to head bond formation. So the actual bond direction is nothing but head to head collision and head to head bond formation is nothing but the ligand accepting through the electron is head on collision, is heated by directly head to head. That is called a actual bond direction. Then steps 3. Up to this point the complex formation would not be favored. This decreasing in the energy is derived from the complex formation is nothing but, so once we have the energy will be splitting, the d orbital would be splitting. This favored for some of the structures. So some of the structures is having a different types of magnetic moment. This magnetic moment helpful to identify the complex formation, whether the complex structure is a tetragonal, bipyramidal, so many structures is available. So once the d orbital splitting will be occur, how the electronic configuration as well as the structure will be occurred, finally the distribution of d orbitals. Now I shown one of the splitting, crystal splitting of octahedral complexes. So the crystal field splitting of octahedral complexes, you should understand first the octahedral complexes is nothing but this is central metal atom, this is one ligand, as well as this is one ligand, this is one ligand, and this is one ligand. These 4 ligands is having a same space. Same space means same plane. Whether this is a top and this is a bottom. So this totally is having a 8. 8 means octa. So the structure is called a pyramidal. Pyramidal structure is simply one side means we said pyramidal, the both side means hedral. So octahedral. The octahedral complexes is nothing but see the ligand is the complex is containing a 6 ligands. Okay. So 6 ligands is containing when you should understand that is called a octahedral complexes. So this is a ground state of octahedral complexes for a d orbital. What are the ground state d orbital substances there? dxy and dyz and dzx and dxy minus y square and dz square. Suppose the ligand is come and approach the d orbital, the energy will be moving little bit high. Okay, this is a normal metal. This is ligand approached complex. Okay, now the ligand is ability to donate a pair of electron. The splitting will be occur. The splitting will be occur. How the splitting will be occur? The low energy orbitals is coming to the ground normal state or lower end, the high energy orbital is going to the higher end. What are the higher end orbitals? What are the lower end orbitals? Along with the axis, orbital is always higher energy, because I said that the direction would be axis, direction will be happen only along with the axis. So only we said a dx square minus y square dz square, especially in octohedral complexes, this is having a higher energy. So only splitting is more. So only the splitting is more. That normally the in between the axis orbitals is coming on lower end, because the electron moving through the only axis, so in between the orbital electron revolving is not able to accept. The along with the axis orbital is having a higher energy. What are the higher energy orbitals? Dx square, dz square, dxy and dyz and dzx is nothing but a lower energy orbital, because it's having a in between the axis. This two is having a along the axis. What I said earlier, this is Eg set. Higher energy is called Eg state. That lower energy is called a T2G set. Okay. Now the totally splitting will be happen. Now we are going to identify how many splitting will be occur. So this is an Aragon approach to a complex formation d orbital. This orbital taken as a center, or taken as a center. This whole splitting we are considered as a 1. Whole splitting we are considered as a 1. Okay, what happening? The splitting will we are going to identify the in between the axis we are making a line. This line, the normal complex formation ligand line, is called a berry center. Berry center is nothing but a complex formed center is called a berry center. The berry center is helpful to identify the how many splitting will be occur to the d orbital. This orbital is having a maximum splitting. This orbital is having a lowest splitting. I said the earlier, the reason is this dx square minus y square and dz square are having a along with the axis orbital, so only is having a higher energy. The dxy and dyz and dzx is having a lower energy due to that in between the orbitals. Okay, so finally is having a zero point 0.6 plus 0.6. This having a minus 0.4. It totally we should say that splitting is maximum for the along with the axis orbital. So you can understand the students, the octahedral splitting, the Eg set on top, the T2G set on bottom, the higher energy orbital for the dx square minus y square and dz square. The lower energy orbital is dxy and dyz and dzx is called a lower energy orbitals. Now I'm explaining in the earlier slide, I explained octahedral. Now I'm going to explain the tetrahedral complexes. Okay, what is the speciality for tetrahedral and octahedral means? This is the tetrahedral structure. This is a central metal atom. These three atoms, these three ligands in the same plane. This is on the top. Totally, we say this is a tetrahedral complex. The tetrahedral complex beautiful example is methane. Okay, now I'm going to see the ground state of tetrahedral complex at the orbital. The same orbital I took. This is a complex formation orbital. This is a berry center. Now I'm going to explain the splitting of d orbital. See, the splitting of d orbital is nothing but check the tetrahedral complexes. In between the axis only the electron will be donating to the ligand. So here the in between the axis, what are the orbital is there for the in between? dxy, dyz and dzx is having a in between axis, so only is having a higher energy. Along with the axis is no electron will be shared, is coming from the lower energy. In tetrahedral complex, you make a difference between the octahedral and tetrahedral. The octahedral splitting will be high due to the along with the axis, but the tetrahedral high is between the axis orbital only higher energy. Though now we are explaining T2 and EG only for this complexes, because we are not able to explain the complex formation in between the axis. So only T2 and EG. Delta T plus 2.5 by the value. This is a very center. Then dx square minus y square 3 by 5 delta t. Totally overall the D2 energy will be high to the tetrahedral complexes. So the now crystal spill filtering energy and nature of the ligand, I said the earliest in VBT also, depends upon the electronic field, whether they're going to approach a strong ligand, whether they're going to approach a weak ligand, whether maybe a neutral ligand, depends upon the electron donation of the ligand, the splitting will be occur. So the splitting will be occur means we know the sequential arrangement of ligands. Now I'm going to explain the sequential arrangement of ligand. So I said, see, you know that this is a strongest field of ligand, this is a weakest field of ligand, and this is a neutral field of ligand. Three types of ligand field is there. This is strong, this is weak, and this is a neutral field. So iodine, bromine, cyanide, chlorine, the halogens is also having a weak, because it's having atomic molecules is very high. The electronic pair repulsion will be occur very high. This is the smallest molecule, the ability to donate a pair of electrons very easily, and complex formation also very easily. So why we want to focusing this many distraction, this many things for the distraction of d orbital means d orbital gives to the color to the complexes. Okay, now we are going to see the how the d orbital giving a color to the complexes. A substance exhibits colors which absorb the light of a particular wavelength in the visible region and transmit in the rest of the visible region. One color wheel is there. Here the original color and complementary color is there. It's a simple concept of this one. We are observing a one color and replying a one color. So absorbed color is a parent color, replying color is a complementary color. So we are human eyes also having a capability to like this only. We are observing one type of light and replying a complementary light. So this is a color wheel. We are having a 6 that VIBG or orange, yellow, green, blue, violet and red. So what is this NM means? NM is a nanometer. This is a absorbed frequency wavelength or frequency wavelength. Okay, usually we can check that absorption in Armstrong also, but nanometer also, wavelength also. Okay, this you can understand the color wheel. Suppose your compound is absorbing a orange light, is going to reply a blue color. You can understand the copper sulfate is having a blue color, so is absorbing a orange light. His complementary color will be replied. Your compound is yellow, but violet color will be repelled means the complementary color will be replying. The two sets of orbital is there. I said earlier, the T2G and EG for the octahedral complexes. The role of T2G and EG is when the white light fall on the complex ion, the central metal ion absorb the visible light. Okay. Suppose that the distortion will be happen. The T2G orbital is a bottom and EG orbital is on a top for the octahedral complexes. We are fall to the light to the sample. So it's absorbing a white light and is absorbing a white line's visible light corresponding the crystal field fleeting transmits the rest of the light which is responsible for the color of the complex. So white light is absorbed means is able to transmit a complementary color. The complementary color whether they may be blue, green, yellow or whatever it may be. But we are passing a white color. The white color is not able to give any complementary color. So only we are analyzed for a white light as a source of complementary. Some of the tabulated things are given here. Wavelength, wave number, color of observed color. Okay. The 400 Armstrong. A naught is a Armstrong. The wavelength V is observed by the centimeter inverse. The both units are, you can write any one unit is enough for that. Whether we are going to write a wavelength or wave number. Wavelength or wave number. Okay. Suppose we are passing a wavelength is nothing but we are supplying a white light frequency. This also we are supplying a white light frequency. 400 Armstrong light will be passing through the complex. Its color will be absorbed from that complex is violet and reflecting the color is yellow. So 6500 wavelength is absorbing from that complex, that is replying from the absorbing from the red and replying from the blue. These are the complex transmission will be occur. This is absorbed wave frequency. This is a frequency related color. This is a transmitted color of the complexes. So I take one example for titanium hexa aqua 3 plus as an example. What is the speciality for this one means titanium is a D1 oxidation state. H2O is a neutral ligand. So the absorption causes excitation of d orbital of the central metal ion, form a lower energy T2C level of the higher energy Eg level, which known as DD transmission. So it's an important point. Sometimes they're asking what is meant by DD transition is nothing but absorption causes excitation of d orbitals of central metal ion, form a lower energy T2C level to higher energy Eg level, which known as DT absorption. So I took a titanium hexa aqua 3 plus as an example. So the titanium is having a only one electron, okay, only one electron for dxy. This fully 6 electrons is going to filled with the d orbitals, okay, but actually we are having a 5 subcells only. DD transmission occur at a lower range because it's a weak neutral ligand field. This ability to donate electrons filled with this one means that is enough. Okay, the splitting energy will be delta 0. 0 is nothing but adu, that is O. Now don't mention 0. Delta O is equal to O means octahedral 239.7 kilojoules per mole. So this much energy will be emitted. This much energy will be emitted for your DD transition. How the absorption is taking place, but some of the complex coordination complex, why that is not having the colors? The complex of central metal atoms such as scandium 3 plus, titanium 4 plus, copper plus, zinc 2 plus, etc. are colorless because the electronic configuration of scandium is to 1 plus or 2 plus is enough. 3 plus means the beyond the oxidation state they are losing the property of a coordination compounds, so only is not able to give any absorb the color, but it's not able to give any complementary color for the compound. So in this type of compound the DD transition is not occurring. The complex within the central metal having a D0 or D10 configuration. So this is also a D0 to D10 configuration only for the absorbing a color and reflecting a color, but this is not coming that D0 to Z10 configuration level. So I shown some of the complex. This is chromium colored complex, like n number of colored complex in your coordination chemistry. These are the colored compounds. Why the color is not occurring means this is not coming this configuration, okay. This and all coming D0 to D10 configuration. Thank you students.